both academic research and industry with considerable potential of applications in everyday life. The use of catalyst technology is well known from ancient time, although the concept of catalysis was not clear at that time, but they used to do formation of alcohol from sugar by the process of fermentation, synthesis also by hydrolysis of animal fat, converting of alcohol to ether, catalyzed by sulfuric acids, and much more. The term catalysis was coined by Swedish chemist Berzelius and Oswald in 1895, scientifically explained it as a catalyst that accelerates a chemical reaction without affecting the position of the ingredient. In 1909, Oswald was awarded the Nobel Prize for his pioneering work in this field. As my work is concerned with the synthesis of photocatalysts, so let's talk about the phenomena. Actually, what happens when the photocatalysis occurs? In particular, the activation of photocatalysis is achieved by means of absorption of photon of ultraviolet energy resulting in the promotion of an electron from valence band into the conduction band and simultaneous generation of a positive hole in the valence band. This phenomena is generally called charge separation, and it means the generation of electron in hole pairs. These pairs may be combined using heat, or they are able to promote reduction and oxidation reactions with the species absorbed on the catalyst surface. As far as work is concerned with the synthesis of graphene oxide based heterogeneous photocatalysts, so graphene oxide is a single atomic layer material with various oxidation containing functionalities such as epoxide, carboxide, and hydroxide group. This works with it more and easy to process. Graphene materials can be used as either the catalyst or catalyst approach due to their excellent mechanical properties, high stability, durability, and high thermal and electrical conductivity, making a promising photocatalyst or photocatalyst support option. Problem statement. The indiscriminate production and consumption of carcinogenic and hazardous organic compounds has resulted in severe contamination of water bodies. Therefore, the removal of carcinogenic compounds causing contamination through conventional with the assistance of graphene-based materials as they show their unparalleled flexibility in tailoring their properties. Experimental work for the synthesis of graphene-based graphene catalyst. The first step was the synthesis of graphene oxide that was synthesized by modified Haber's method. Then catalyst synthesis. This slide shows the procedure for the synthesis of graphene oxide by a homogeneous catalyst. Photocatalytic degradation experiment for the degradation of bisphenols. The photocatalytic performance was done under UV light irradiation condition for the catalytic degradation of bisphenols. Likewise, bisphenols photocatalytic experiment for the degradation of selected titanic and anionic industrial dyes were done under average conditions. Results in discussion, characterization. FTER analysis, Fourier transform infrared spectroscopy is an analytical technique that is used to determine the functionalities of any specific material. Here, figure A shows the FTER spectra of our synthesized graphene oxide, and here the results describe that the oxygen-containing functionalities like OH stretching at 3400 centimeter inverse, carbonyl stretching at 1700 centimeter inverse, and CO damping at 1130 centimeter inverse confirm the successful synthesis, while figure B and C shows the FTER analysis of our synthesized composite and represents the confirmed successful synthesis. XRD analysis. XRD analysis was done in order to check the crystallinity of our synthesized material, and from these XRD profiles, it has been confirmed that our synthesized material are highly crystalline in nature, which has been further confirmed by cell analysis. Scanning electron microscopy is an analytical technique that is used to determine the morphological structure of any specific material at different magnification scales, and from these results it has been evident that our synthesized material is crystalline and highly porous, spongiform, and possesses a large morphology and structure. So hence we have named our synthesized material as sulfated activated expanded geofloss that has been formed after the microwave treatment. BET analysis was done in order to check the porosity of our specific material. This BET analysis of graphene oxide shows the surface area of 1.006 meters square per gram with 1.86 nanometer per diameter. This slide shows the BET spectra of our synthesized material. This slide shows the BET analysis of our synthesized material after the microwave treatment. And here we have observed that our synthesized material possesses enormous increase in the surface area of 500.3 meters square per gram with 3.90 nanometer per diameter respectively. This analysis was done in order to check the elemental composition of our synthesized material. This slide shows the ABS analysis of GEO. This slide shows the ABS analysis of our synthesized material, which has confirmed that our synthesized material has been successfully synthesized. Now, setup potential was done in order to check the charge processing capability of our synthesized material. Now, operational parameters for catalytic degradation of bisphenol A using UV visible light, and different parameters were optimized for the catalytic synthesis of bisphenol A, like pH time, steady catalyst amount, dosage, and concentration. Like bisphenol A, same procedure where different parameters were optimized for the photocatalytic degradation of other selected organic contaminants, like bisphenol S. Methylene blue, methylene violet, methyl orange, Congo red respectively. This slide shows the optimized parameters for our selected organic contaminants and have found maximum catalytic degradation and found the good catalytic activity of our synthesized material. Same procedure was followed for the real wastewater sample analysis. Photocatalytic activity was done in order to check the efficiency of our synthesized material in real wastewater samples, and with the results found that good catalytic activity of our synthesized materials towards the optimized parameters in real wastewater sample analysis. Study of degradation patterns of bisphenols. This slide shows the operating parameters of GCMS. This slide shows the GCMS product now. So please, concluding on the so in this study, nickel sulfate integrated expanded geoflowers were successfully synthesized by simple process using microwave. Different characterization techniques were used to study morphological and chemical characteristics of synthesized nickel sulfate integrated expanded geoflowers. Some images reveal excellent expansion of graphene oxide via microwave treatment. We further confirm the enormous increase in the surface area of our synthesized expanded nickel sulfate integrated geoflowers. After microwave treatment, setup potential charge distributed data shows the negative charge of the area of our synthesized composite that further confirms the non-agglomerative nature of the prepared material. Different parameters such as pH time, amount of catalyst were optimized for maximum degradation of bisphenol A and its analog bisphenol S using nickel sulfate integrated expanded geoflowers using UV light irradiation, and maximum degradation was obtained in pH 4 and pH 8 respectively in 20 minutes using 0.05 gram per liter of catalyst. The catalytic efficiency of synthesized nickel sulfate integrated expanded geoflowers was also analyzed by degrading different catalytic and inorganic industrial dyes under ambient conditions. The prepared material showing excellent degraded bisphenol S were proposed. The degradation efficiency of synthesized nickel sulfate integrated expanded geoflowers was also evaluated using real wastewater samples obtained from industrial waste. The prepared material showed good catalytic activity in real samples.